Hello, this is the second chapter of visualization of complex integration with GeoGebra. Section 4, Fundamental Theory of Complex Integration. D is a domain in the complex plane. Small fz and big fz are complex functions in D. If big f-z equals small fz everywhere in D, for any curve C in D which joins alpha and z, fz over c dz equal big fz minus big f alpha. The value of integral only depends on alpha and z. It is independent from c. Therefore, if alpha equals z, if c is closed, integrates fz over c equals 0. This is very similar to the fundamental theory of the real number function. Like alpha to z 1 dz. You can't write this unless, without the fundamental theory, because normally it depends on the curve. So you have to specify the curve. But so here, because there is a primitive here, it's called big fz is called the primitive function of small fz. Because there is a primitive function of 1, so you can just write alpha to z. Similarly, alpha to z, z dz equals z squared 2 over minus alpha squared over 2. Alpha to z, z squared dz equals z cubed over 3 minus alpha cubed over 3. Note, there is no primitive for 1 over z, because alpha to z 1 over z can change with the path c from alpha to z. Which means that there is no primitive of 1 over z whose derivative equal 1 over z everywhere on the complex plane. Very rough proof of fundamental theorem. Since big f dash z equals small fz, when zk plus 1 minus zk nearly equals 0, big fzk plus h minus big fzk equals small fzk, zk plus 1 minus zk. So, small fzk, zk plus h minus zk nearly equal big fzk plus h minus big fzk. When you sigma, which is equivalent to big fz2 minus big fz1 plus big fz3 minus big fz2 dot big fzn minus big fzn minus h. And these sums are cancelled. So only big fzn minus big fz1 remain. So this is a very rough proof. Do you understand which is wrong? Because when zk plus 1 minus zk close to 0, these two get very close. But the number of n increases. So each error becomes very tiny, but the number of elements also increases. So it's a problem of infinity multiplied by 0. So you can't tell. So, it's an indefinite limit. Okay? So it's not a real proof. But you can understand this theorem well, because from that proof, this theorem, holds true as long as the path is in D. So if there are holes, it has nothing to do with this. As long as you can go through the, green plane, it's okay. Even if there are holes and mountains, as long as you can walk on green path, that's fine. The integral is big Fz minus f alpha. Okay? Now that we can find the value of this integration, which is the same integration of the last time. The last time we are discussing that it is very difficult to find the value if we follow the definition of the integration. Fz equals z squared, and the curve is here. But Fz has a primitive, which is z cubed over 3. So it is very easy to find the value. First, we have to change the properties to complex number, and then f cubed over 3. Okay, this is a value. Oops. Okay. So, not very close, but we can make it closer. Okay, we'll do very dangerous. Okay, it gets closer. Section 5, integration of 1 over z minus a around the circle. In the previous section, we discussed that there is no primitive of 1 over z, but integration exists. It only varies in accordance with the path. Here we are going to find the value of the integration. When z is on the circle C of radius r centered at C, and the theta is argument of z minus a, then z is parameterized by z minus a equal r cosine theta plus I sine theta. Then dz equal r minus sine theta plus I cosine theta d theta. And this part is equivalent to this part multiplied by I. So dz equal I z minus a d theta. Therefore, we get dz over z minus a equal I d theta. And this formula is very important. So we are going to see this with Okay, alpha is center, z is on a circle, and this is dz. And they are same. They are just translated to the origins. So first we are going to find the argument of dz over z minus alpha, which is argument of dz minus argument of z minus alpha. But when d theta becomes very tiny, these two vectors become perpendicular. So the argument of dz minus alpha nears 90 degrees. So next, length of this vector. Length of dz equal length of z minus alpha d theta. Therefore, length of dz over z minus alpha equal d theta. So length is d theta. Argument is 90 degrees. Thus, dz over z minus alpha equal I d theta. Okay, these two are same. So if the C is a whole circle, and if we integrate this over C, it is equal to 0 to 2 pi I d theta, which is twice by I. And it doesn't depend on the R. Now it is r equal 1, but if we increase r, z minus alpha, the length of z minus alpha increases, but the length of 1 over z minus alpha decreases. So dz over z minus alpha doesn't change as long as d theta doesn't change. Now its d theta is 0.2 radian. It's almost fifth of this length. So from our eyes, we can, see that dz over z minus alpha equal I d theta, which is 0.2 I. Okay? So like we saw with the GeoGebra, if the curve C is this curve, integration over C is I theta. If the C is a whole curve, one circle, then the integration is twice pi I. So it looks like integration is unique, but it's not. Because to reach Z, you don't have to go this way. You can circle one more. This one. If you circle like this, integration is I theta plus twice pi I. So there is always a twice pi I n difference between these integrations, even if z is the same point. That's why the primitive doesn't exist. Section 6, Cauchy's integral theorem. This is the most important theory of complex integral. If fz is analytic everywhere inside a curve C, that is, if there is no singular point inside C, integration fz dz along C equals 0. A singular point is a point where fz is not analytic. Cauchy's theorem can be applied to C1. Fz is analytic in the shaded area, and there is no hole, no singular point inside C1, so Cauchy's theorem can be applied. But it can't be applied to C2 because there is a hole. For example, integration of 1z squared dz along a unit circle equals 0 because there is a primitive of 1z squared, which is minus 1 over z. But it's not implied by Cauchy's theorem. It is implied by the existence of a primitive. So the fundamental theory and Cauchy's theorem are very similar, but they are different. Fundamental theory is more like one-dimensional theory. The value is 0 as long as the path lies inside the shaded area, and if there is a primitive, the integration is 0. But Cauchy's theorem says that there can't be a hole inside. If there is a hole inside, it can't be guaranteed that integration is 0. So they are very similar but different. Example, fz equal 1 over z is analytic except O, okay? Therefore, any closed curve C which does not enclose O, integration is 0. There is no primitive of 1 over z, but as long as it doesn't have O inside, integration is 0. Very rough proof of Cauchy's theorem. It's very similar to the proof of fundamental theorem, but with fundamental theorem, we divide the path into many tiny sections. But instead of dividing the path, we divide the area. We divide the area inside C into very tiny areas. And we prove the integration along the edges near 0. So the proof basic idea is very similar, but it takes time to explain this. So I write down the links to all the files I used during this presentation, including GeoGebra worksheet. So please read it by yourself if you're interested in. Is that okay? Thank you very much. Section 7, deformation of the path. Fz is analytic inside C, except these 2 points, Z1, Z2. And we make tiny circle C1 and C2 like this. We also make this long path, but which doesn't have Z1, Z2 inside. So by the Cauchy's theorem, this integration equals 0. But T1 and T2 are very close and opposite direction. Integration along T1 and along T2 are cancelled. Also, T3 and T4 are cancelled. So the left hand side only remains these integrations. So we get this result. Integration Fz along C equal integration Fz along C1 plus along C2, which means this integration along C1, C2 equal to the integration along C. So we can deform the path as long as it doesn't cross singular points. As long as you don't cross the singular points, it's like a string. As long as you don't cross the singular points, you can deform the path as much as you like. Okay? This is called the deformation of the path. Let me explain this way, because this is very important. You build poles on the singular points, like this one. And you can move a string on the complex plane, but you can't lift it. So you can move this path to C2 or C3. And you can move C1 to C2. And in addition, 2 paths running along in opposite directions can be cancelled. So you can integrate along C3 instead of C1. This is an image of deformation of a path. Let's check the deformation of path with GeoGebra. Fz equals 1 over z. A singular point of Fz is origin. And the path is from A to A and clockwise. This is the path. So it doesn't include singular point inside. The integration should be 0. Okay? But if we move D to the left, integration changes all of a sudden. Okay? And the value doesn't change as long as it doesn't cross the singular point. This is the deformation path. As long as it doesn't cross the pole, the value doesn't change. Why twice by I? Because the integration along this curve is equivalent to the integration along a circle, which is twice by I. So that's why the integration is twice by I. Get it? So thanks for watching today. Next chapter is Cauchy's formula, and that is the end chapter of the basics. So I'm very looking forward to seeing you again. Bye bye.